So now we have some basic concept about the electric potential and the potential energy. So we try to calculate some more complicated situation. Okay, this is the potential due to a charged particle. This is similar to the electric field. It will not relate to the test particle itself, the Q0 itself. It only relates to this Q. Whenever they are charged, no matter positive charge or negative charge, in the space there will be some potential. There will be some electric potential. And we can define the potential difference like this. For radial path, we can do this integration. For this case, we want to place the particle from infinitely long away to R. R is the distance between Q and the destination of Q0. And actually, as we know, E would be this one. E will be this one. 1 over 4 pi epsilon 0 Q over R square. And we set Vf to be 0 at infinity. And Vi will be V, so that after this simple integration, the voltage at this point will be 1 over 4 pi epsilon 0 Q over R. So for F, it is Q1 times Q2 over R square. For E, it will be Q over R square. For V, it will be Q over R. And for potential, in the coming slides, it will be Q1, Q2 over R. So there are 4 of them. They are good friends. Okay, so I think, yeah, one point to mention is that potential is a scalar. The force, the electrostatic force, and the electric field are vectors. This is scalar, and so as the potential energy, the U. So when you try to calculate the potential due to a group of charged particles, which means you have more than one charged particles, the potential due to the a collection of charged particles is the summation of all of them. And you may say for electric field is still the same. You calculate the electric field generated by one charged particle, and then you add all of them together. But actually, for this case, you still add all of them together, but this time you add many scalars together, which will be more simple. When you try to add some vectors together, you need to separate in x direction, y direction, and then you add x direction together and the one in y direction together, so that it will be more complicated. The potential is algebraic sum of the individual potential with no consideration of direction. So it will be more simple. So this is Chap 3. The figure here shows 3 arrangement of 2 photons. So 2 positive charge Q or E. Rank the arrangement according to the net electrical potential produced at the point P by the photons greatest first. Think about it. That's the potential of at point P. arrange them in order from largest to smallest. Actually, this is small d, large d, small d, large d. Who would like to get the bonus? Just try. If you answer incorrectly, there will be no punishment. Anyone want to try? No one wants to try. This is not difficult. You don't need to capture anything. Actually. Bonus, who want to try? Actually, it may worth a lot because only she have tried once, so. Others, any others want to try? And to vary some with no consideration of direction. 1p is here. Okay. 写好。This is a little bit tricky. If only you answer 10 questions throughout the whole semester, it won't worth a lot. If 10 students answer one question throughout the semester, it may worth a lot. This is really tricky, so you don't try to answer all the questions. It may not be as good as give others some chances. So actually, the potential at P for A, B, C are the same because this one is small d, large d. So for that equation, Q1 and Q2 are also E, and R1 would be small d and large d, and so as these two. So actually, from potential point of view, they are the same. If you consider the electric field, they are not the same. If you consider the electric field at point P, and point P, they are not the same because for electric field, actually for this one pointing this way, for this one also pointing this way, so that they add together. And for this one, this one has an electric field pointing this way. This one has E field pointing this way. So overall, it will point to that way. And for this one, they will cancel part of it. Okay, next sample. So what is the electric potential electric potential at point P at the center of the square. Okay, point P at the center of the circle. Okay. Electric potential, okay. Electric potential here. The distance d is 1.3 meter, and the charge are Q1 plus 12 nanocoulomb and so on. So, okay, R would be d over square root of 2, similar to that. Actually, 45 degrees, so this is d over square root of 2. And V would be summation k equals 1 to 4 bk. So it will be 4 pi epsilon 0 q1 over r plus q2 over r plus dot 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 plus q4 over r. So quite simple, and we substitute all the stuff in. 8.99 times 10 to minus 9 times square root of 2 over 1.3, and this is 12 minus 24 plus 31 plus 17 times 10 to minus 9, which will be 350 volt. So actually quite simple for this example. And this graph shows that, actually this is the answer, show that the equal potential surface will be something like this. Don't ask me why it will be like this. And actually, if you calculate the potential for every point on the plane, then you can draw this line, and it will be something like this, because Q2 is negative. Q2 is negative, so that this curve will be somewhere like here. But I can't tell you why it will be curved like this or like that. So for this one, 12 electrons of charge minus E are equally spaced and fixed around a circle radius r relative to V equals 0 at infinity. What are the electric potential and electric field at the center of C circle due to this electron? Okay, for E field it is simple. E should be 0, because this one will cancel with this one will cancel with this one, and etc. etc. So all of the E field will be cancelled. But actually the V will be, you add all the potential together, so that it will be something like 1 over 4 pi epsilon 0. Everyone is minus E, so totally minus 12E over capital R. So very simple. For B, if the electrons are moved along the circle until they are non-uniformly spaced over a 120-degree arc, what then is the potential at C? The potential is actually the same, because they are just scalar summing. So actually, actually the potential would be the same, but at this time E would not be 0, but I cannot calculate because it doesn't tell you where exactly every dot is. So I think this is a easy demonstration for the electric potential. Any questions up till now?
比如说一不等于零，不用说它指向左侧，不用。
指向左侧大概吧，因为你也没法算它具体指向哪个角度，所以做也没什么意义。How does it change? Okay, so this is potential due to a electric dipole. So I hope you can still remember what is a dipole. Basically, there are two charges, the same magnitude but opposite sign. One is positive Q and another one is negative Q. They have a small distance d. So now we want to calculate the net potential at point P. At point P here. So actually, okay, because there are two charges, so the total net potential is V plus V minus. So for the positive particle, it will Q over R plus, which is this distance. And another one will be minus Q over R minus. So up till now, don't care about what is R plus, what is R minus. And okay, we can factor small q out, and we add these two terms together. So this one will become R minus minus R plus over R plus R minus. Something simple. Up till now, I think we can approximate these two lines P as being parallel and their length distance as being the leg of a right triangle. Actually, we assume this point is far away from this dipole, so that we can assume these two lines are parallel with each other. Then R minus R plus will be this segment within a right angle triangle. So actually, this is theta, this is d. So this segment will be d cosine theta, like this here. For R plus times R minus, we can approximate it to be R squared, small R squared, which is counting from the middle point O to P. This is R. The green one is R plus N. This one is R minus. But if P is far away enough, then we can approximate they are the same. But actually, we cannot approximate R plus R minus equals R plus for this term. If otherwise, it will be 0. Then it means nothing. So we substitute these two terms into here. Then the voltage potential will become this. Very simple algebraic calculation. And if you can remember the electric dipole moment P equals to QD, so that we can group this together as P. So this equation will look like this. So we come to more fancy math. Potential due to continuous charge distribution. So for continuous distribution of charge, we cannot add them together because they are continuous. We cannot count them. So as usual, we separate into infinite small element and then we integrate them. So the equation can be written like this: V equals integral of dV, and it will be look like this because these terms are constant. So we consider infinite small charge element. Each element will have a phase distance for consideration. So we integrate this term. So potential due to a continuous charge distribution, line of charge. Okay, for this rod with length L, and the line density is lambda. So dq will be lambda times dx. Dx is a small length shown here. Dx is small length, and times the density will be the small charge. So we try to integrate this stuff, and for R is what we want to consider. R is the distance from the point we want to consider to the infinite small element. This is R, and this is the x direction, and so R will be square root of x squared plus d squared. Something like this, and subtract this to substitute this to here. So dV will look like this. So now we find the total potential V. So we integrate this. We integrate this. So if you look at the textbook in Appendix E, if you integrate this term, it will look like this. Do you want me to show how to derive it? Actually, this is not difficult. You only need to substitute but actually don't worry too much. I won't let you derive in the exam. So actually, basically this is a standard process because you have sorry. Because you have a term x squared plus d squared. So actually, you need to define x will be d tangent theta, so that you have the term 1 plus tangent square. So it will become something like dx will be d secant square theta, and actually x squared plus d squared will be d secant theta. This d is not that d. This d is different. This is actually this d. This one for this one. This is the d for the derivative. That d is this d. So okay, you can write, you can draw a y-angle triangle. This will become theta L, and this is L. This is x squared plus d squared, and this is no. This is L. L. This is D. This is D. As you want, tangent theta will be L over D. Tangent theta will be L over D. So this one will be L squared plus D squared, and take the square root. So this integration will become this way. D secant square theta. D secant theta. D theta. Okay, you put all of them into the original one. Because this one, you have a negative sign here, so at the bottom. And dx will be, dx is like this. I forgot d theta, d theta. D theta. D theta should be here. D theta should be here. Because dx, you substitute the variable, so it still have d theta here. So this is this term is dx. And this one will be this one. So it turns out will be like this. Theta 0, secant theta, d theta. And you multiply secant theta plus tangent theta. You multiply secant theta plus tangent theta. So it will become like this. Secant theta plus tangent theta. D secant theta plus tangent theta. So it will become log secant theta plus tangent theta. Theta L 0. So finally, it will become, go back this way, log tangent theta L plus secant theta L minus log 1 plus 0. Tangent 0 is 0. Secant 0 is 1. So this one is 0. And you substitute theta L, tangent theta L to be L over D, and secant theta L to be this one over D. Then it will become this. So this integral is not too difficult. Well, maybe we go. Okay, we will. Okay, we still have 15 minutes. Hopefully we can finish page 20. So for this page, it is a potential due to the continuous charge distribution. 3. We try to calculate the potential from a charge disk. Okay, similar as before, we try to separate the disk into many rings with different radius. So the Q, the charge in this ring will be something like the density multiplied by the this circle will be 2 pi r prime, and actually the height of this ring will be dr prime, the height. So we try to cut it, and then it will look like a rectangle, and then the width will be 2 pi r prime. The height will be dr prime. So these two terms will be the area of this orange ring multiplied by the density, the upper surface area. So dV can be written like this, and actually R is this one. R is this one from P to this ring, and so R is equal to Z squared plus capital R squared. Actually, there are some typo mistake. I think there are a few typo mistakes in this page. I just let you know. This one should be R prime squared. This one should be R prime squared. And dq is the upper one, so nothing special. And we find the net potential at P by adding via integration. So the total V will be the integration of dV. So actually it is look like this. Actually, yeah, 4 pi, 2 pi and 4 pi is reduced to be 2. So 2 epsilon 0 here. Sigma is a constant. So dr will be here. And r prime is here. And actually, similarly, this one should be r prime squared. And this L should be R, should be capital R. This L should be capital R. So there are 3 typo mistakes in this size. So this one should be R prime, this L should be capital R, and this R is also R prime squared. So for this term. Actually, for integrating this term is simple, I think, because two r prime dr prime should be dr prime squared, something like this, and it should be equal to 2 r prime square plus c squared. This like this, because z is a constant for the integration. So you have this one, and this one is something like this to the minus 1/2 power. So the integration is simple, and you can get the final answer easily. Actually, yeah. Well, okay. We'll have some slides. Recalling this. So for calculating the field from the potential, actually, if we put a positive test charge Q0 in the field, moving through a displacement ds from one equal potential surface to adjacent surface, the work the E field does on the test charge during the move is minus Q dV. Is this term? And also for the mechanics point of view, the work done is also F dot ds, and F would be Q0 times E. So we can equate this term and this term. It will become like this. And finally, we reduce Q0 on both sides, and the rest of the stuff will be E cosine theta equals minus dVds. The derivative of the electric potential with respect to the displacement. And actually, you can regard E cosine theta is a projection of the E to the S axis. So we finally write it like this: ES equal minus dVds. The derivative of V along the S-axis. So actually, it is something called the gradient theorem, or the fundamental theorem of calculus for line integral, as present in the previous slide. We have V equals this term, and actually we can write it as E equals the negative gradient of V. For this one, it is in one dimension, but generally we can write it as 3 dimensions. In the textbook, it only shows these 3 separately: Ex equals minus dV dx, Ey equals minus dV dy, Ez equals minus dV dz. But actually, you can write it like this using the gradient. Actually, it's just the derivative in multi-dimension. So it's just a notation. Don't be afraid of it. Derivative, but do it many times. So the point we define the electric potential is that, suppose we calculate the total potential will be easier because it is scalar summation. So if we can calculate the electric potential for the whole space, and then we take the gradient, we can calculate the E field, which will become a more complicated one to calculate if you separate our many charge and then we calculate the E field from each charge and then summation sum. But actually, we calculate the overall electric potential first, and then we take the gradient. And actually, it's similar for one variable. It will simply like f of x dx ab equals f something like this, and okay, we maybe this one should be x, so this is x. Maybe I just x. So this is the fundamental theory of calculus. So dfx will be f of x for one variable. For one variable, the derivative of capital F will be small f of x, and the integration of small f of x from a to x, maybe x prime here, then it will become capital F of x. This is the multi-dimension cases, which is called the gradient theorem, as known as the fundamental theorem of calculus or for line integral. Okay, maybe